Hey guys, welcome back to my channel. Today we're going to talk about the heap memory versus stack memory. So heap and stack are two types of memory storage in the computer systems, often used to manage memory allocation and deallocation during program execution. So let's see what stack memory is and what heap memory is. So stack is a region of memory that operates in last in first out manner. It is generally used for static memory allocation, primarily for storing function calls, local variables, and the control flow information. So as a stack data structure, which always has the last in and first out, right? So it is generally used for storing the local variables in a given function. It's also used to store the information about the parameters that are passed to a function, the return address of a function, and the control flow information. So let's say we are running a program that calls a particular function, and that in turn calls another function. So that particular inner function, when it is called, the parameters that are passed to it, the return address to that particular function, and the local variables in that function will all be stored onto a stack frame. Okay, and once the execution of that program is that particular function is over, it will be popped out of the stack, and then we go back to the previous function. Again, once the execution of that particular function is finished, again we'll pop it out. So this is also something how recursion works. So this is what the stack memory is generally used for. Heap memory is more of dynamically allocating memory and deallocating it. It's used for storing data structures whose size and lifetime cannot be determined at compile time. So generally the memory which is stored onto the stack, these variables, the static variables, right? So these, during the compile time, the compiler will decide like how much memory should be allocated for these particular variables. But dynamic memory is something which we do not know until the program is run, and how it will be affected over the period of time. So that's when we use the functions like malloc, memory allocation, calloc, contiguous allocation. Then we do a realloc as well if you want to readjust the memory size. So let's consider an array which is of size 10, which we declare it in the program. Okay. So during the compile time, when the compiler compiles it, it knows that this is a static variable, and the amount of memory that will be associated with that particular array variable will be size 10. But let's say it's a dynamic memory which we do, which we dynamically allocated during the execution of the program, right? So that is something, that memory will be stored onto the heap, not on the stack. Okay, I hope that makes sense. So let's say I just declare a pointer to an array, okay, and then allocate some memory to it. Then once that memory is exhausted, then I want to reallocate more memory to it, so I use a realloc function. So I don't know the exact size before I run the program how much it will end up to. So that's why these kind of memories, generally during the data structures are not, the memory size is not defined uh, before during compile time. It's not statically allocated generally, because in a computer system, let's say like a router or something, right? The routing table will have a, say, a linked list or something which maintains the amount of entries that go in the routing table. If you add more number of hosts, the routing table size will increase. So you generally use dynamic allocation to increase the size of that particular linked list or whatever the data structure you're using. Okay, so the stack memory is handled by the compiler during compile time, whereas heap memory is generally done using malloc, and it is deallocated using free. Okay, now the size of the memory on the stack is usually limited, and it is determined during the compile time. The variables stored on the stack have limited lifetime tied to the scope of that particular function. Heap memory is generally more flexible in terms of size because you can dynamically allocate and deallocate it, and it also has a longer lifetime because these data structures or variables, they generally extend beyond the scope in which they are created, okay, until they are explicitly deallocated. So if you do an malloc or calloc of a particular variable, it is very important that before the entire program has completed, you free that particular memory. Okay, that's if you do not free that particular memory and somewhere it is dereferenced or something, then the chances of crashes occurring in your program. Okay, so it's very important that whatever memory you allocate, you always free it. Okay, and then there are chances of fragmentation. So um, during in stack memory, fragmentation is not typically an issue. Okay, since memory allocation and deallocation occur in a very predictable and orderly manner. You know that during compile time you're allocating a size 10 for an array, and you just have to free that at the end of the program or at the end of the function itself, right? Because it's only applicable to that particular scope. But in case of heap, fragmentation can occur over time as memory is allocated and deallocated dynamically. This can lead to inefficient memory usage and potential performance issues. So there are two types of fragmentation that can happen. One is internal fragmentation. Okay, internal fragmentation is when you allocate, say, a size 10 to a particular data structure, but you only use size 5 in a data structure. So let's imagine this memory as a block. Okay, let's consider an array. Okay, with which is dynamically allocated, and the total number of size that you can have in your system, memory you can have in your system is 100. Okay, you dynamically allocate 10 memory blocks to that particular array. Okay, and then you use some memory for some different other variables, some different data structures, and then again you want to allocate 10. Okay, so now let's say you have filled up the 100 spaces, 100 memory block spaces by allocating somewhere, and then after a certain amount of time you deallocate some memory somewhere. Now you want to do a realloc where you want to reallocate a certain size of for your data structure, right? Now what happens is in that 100, let's say you're doing a reallocation for 10 size block. Okay, but that 10 space will not be there because the number of contiguous memory that is left, right, might be 4, might be 5, might be 6, it will be less than the 10. So these are some of the issues that can occur in case of, like, fragmentation. So this is called as external fragmentation, when memory blocks are scattered throughout the heap, making it difficult to find contiguous blocks of memory large enough to satisfy the memory allocation requirement. Okay, this can happen due to irregular pattern of memory allocation and deallocation, where small free blocks exist in between a larger allocated blocks, effectively fragmenting the available memory space. So this can lead to inefficient memory management. This can also lead to there are certain algorithms that are running to manage this memory. Okay, they'll have to do extra bookkeeping and extra maintenance to keep track of the memory. Okay, that will lead to higher memory overhead. There is also a risk of memory exhaustion, right? So you do have certain free spaces left in your memory block, but the reallocation requires 10 size, right? It requires 10 blocks, but the size which are free might be, 3 somewhere, then it might be 4 somewhere, it might be 5 somewhere, it might be 6 somewhere. So in total you have more than 10 blocks of memory left, but it's not contiguous. So this could lead to memory exhaustion as well. Okay, and also you spend more time in allocating and freeing up the memory if it's scattered throughout the memory blocks, right? One particular, let's say an array, it has total size is 25, but let's say 10 is allocated somewhere, that our next 10 is not contiguous, it's allocated somewhere else, and the next 5 is somewhere else. So to free up and to allocate this memory, it takes more time. So this is the differences of heap and stack memory. We'll discuss more about memory when we actually talk about the memory management series in under operating systems. We're going to go in depth about the fragmentation and how this is solved using what all algorithms it can be solved and all of that. Okay, but this is just the basic information about memory because I just wanted you guys to understand, like, how when running a program, how the memory gets allocated and um, how it gets, what kind of memory it uses, whether it uses stack memory or heap memory. So this is something very basic which I wanted you guys to understand before we dive into the main topics of operating system. I hope this made sense, and If you guys have any questions, please do reach out to me in the comment section below. Uh, Please do like, share, and subscribe. And thank you for watching the video.